Welcome, everyone! Have you ever wondered how scientists figure out the exact chemical structure of a completely unknown substance without, well, ever actually touching it? It's pretty wild. Today, we are unlocking the secrets of literally one of the most powerful molecular detective tools in existence. Welcome to this step-by-step explainer. We're going to take our time today and really dive into the details, breaking down the complex physical and mathematical mechanisms behind Raman spectroscopy, using all the source materials. We're going to start from the absolute basics of light scattering and zoom all the way down into advanced molecular symmetry. Let's get started.
Okay, let's look at our roadmap. We'll be hitting 6 main sections today. 1. Basics of light spectroscopy. 2. The Raman scattering effect. 3. Stokes versus Anti-Stokes. 4. Calculating the Raman shift. 5. Classical theory of polarizability. And finally, 6. The mutual exclusion principle.
All right, Section 1. Basics of light spectroscopy. The fate of radiation.
To start, we really need to establish what spectroscopy actually is. At its core, it's fundamentally the study of how light interacts with matter. And this interaction heavily depends on both the material itself and the specific wavelength of the light. Ultimately, this very interaction is what determines which parts of the visible spectrum enter our eyes, and therefore, the colors we perceive every single day. And this brilliantly illustrates our starting point. When light hits a sample, it basically has 4 possible fates. It can bounce right off the surface as reflection, transmit straight through it, or get absorbed entirely. But for the rest of this explainer, we are focusing entirely on that bottom path, scattering.
Moving right along to Section 2. The Raman scattering effect, a molecular collision.
Now, let's zoom in on that specific scattering event and look at what happens during an energetic collision between a single photon of light and a target molecule. Think of this as a dynamic, high-speed car crash, but at the molecular level. When the photon strikes, its oscillating electromagnetic field momentarily polarizes the molecule's electron cloud. This basically shoves the molecule into a higher energy state, forming an incredibly short-lived, unstable complex that we call a virtual state. And because it's so unstable, the photon is essentially bounced off and re-emitted almost instantaneously as scattered light. So the absolutely crucial point here is understanding exactly how that light bounces off. As we see here, most incoming green laser photons bounce off with the exact same energy they arrived with. That's called Rayleigh scattering, and it's perfectly elastic. But in a much rarer event, I'm talking about 1 in 10 million photons here, there is an inelastic transfer of energy. This is Raman scattering, named after the pioneering Indian physicist C.V. Raman, who first observed it way back in 1928 alongside K.S. Krishnan.
All right, Section 3, Stokes versus Anti-Stokes, the inelastic shift.
Let's look a little closer at those incredibly rare 1 in 10 million inelastic Raman scattered photons and see exactly where their energy goes. Notice how the arrows chart the precise energy transfers happening inside the molecule. The green arrows in the middle show the elastic Rayleigh scatter. Basically, what goes up comes down equally. But over on the right, the red arrows show a molecule gaining energy from the photon and resting at a higher vibrational level. Because the molecule kind of stole some energy, it emits a lower energy photon, which we know as Stokes scattering. On the left, the blue arrows show the exact opposite. A previously excited molecule actually loses energy, donating it to the photon, and emitting a higher energy anti-Stokes photon. To synthesize that complex energy diagram, this table neatly compares our 3 scenarios. Because energy and wavelength are inversely related, always remember that, the scattered wavelength actually increases for Stokes since the photon lost energy, and decreases for anti-Stokes since the photon gained energy. Now, here's a super fascinating quirk of physics. Even though pure quantum mechanics dictates that both of these Raman paths are equally likely to occur, reality is governed by the Boltzmann distribution. In nature, the vast majority of molecules are just resting lazily in their ground vibrational state at room temperature. They literally have no extra energy to give. As a result, Stokes scattering, where the molecule takes energy, is statistically far more probable. This makes the Stokes lines much, much more intense, and the primary target for our actual laboratory measurements.
Which brings us to Section 4, calculating the Raman shift, standardizing the fingerprint.
Because the scattered wavelength depends completely on the specific color of the laser used by the scientist, we really need a mathematical way to standardize these molecular fingerprints across different lab instruments. Think about it. If we just measured wavelength, a red laser and a green laser would give us totally different numbers for the exact same molecule. That doesn't work. Instead, by calculating the difference between the inverse of the incident laser wavelength and the scattering wavelength, we get the standardized Raman shift. This is measured in inverse centimeters, and it remains perfectly constant for a molecule no matter what laser you shoot at it. It's a real game changer.
And applying that standardizing formula gives us a beautiful, universal spectrum like this one for carbon tetrachloride. If you look at the x-axis, 0 in the middle is our laser line. We can clearly see the massive Rayleigh peak right in the center and the highly asymmetrical Stokes peaks towering on the right over the tiny anti-Stokes peaks on the left. This perfectly illustrates that Boltzmann distribution we talked about just a minute ago.
Okay, Section 5. Classical Theory of Polarization. Decoding the Math.
We've seen the visuals, but what does this actually look like mathematically at the molecular level? Well, this fundamental equation of the classical theory shows us exactly what's happening. The induced dipole moment of the molecule, represented by mu, is a direct product of its polarizability tensor, alpha, and the oscillating electrical field of the incoming radiation, E. Basically, how much the molecule's electron cloud gets squished and pulled depends entirely on how inherently squishy it is and how hard the laser is pulling it.
Now, when we factor in that the molecule isn't just sitting still but is actually vibrating, its squishiness or polarizability changes as it moves. Expanding that previous equation using basic trigonometry mathematically proves the existence of our three exact frequency components. We literally get a beat frequency. The math spits out the original frequency for the Rayleigh line, a subtracted frequency for the Stokes line, and an added frequency for the anti-Stokes line. It's just a gorgeous alignment of classical mathematics and observable physics.
Finally, Section 6, the mutual exclusion principle, symmetry and rules.
Let's apply a really powerful rule of group theory to these principles to help us decipher complex, highly symmetric molecules. The mutual exclusion principle is an incredible tool for chemists. It dictates that in molecules with a center of symmetry, think of a perfect snowflake, a normal vibrational mode can be either infrared active, meaning it's driven by an asymmetric dipole shift, or it can be Raman active, driven by a symmetric polarization shift. But it can never ever be both. They are completely mutually exclusive.
However, we definitely have to be careful, as this rule has a bit of a catch. Mutual exclusion doesn't guarantee a mode will appear in either spectrum. Actually, molecules like benzene and ethylene have specific vibrational modes that are completely silent. Because of their unique symmetric shapes, these vibrations cause no change in the dipole moment and no change in polarizability, meaning they completely evade both IR and Raman detection techniques.
And that brings us to the very edge of our current scientific mapping. As we wrap up our explainer on this fascinating detective tool, it leaves us wondering, if our absolute best molecular fingerprinting still has blind spots, what other hidden quantum secrets are waiting to be decoded by the next generation of light scattering techniques, right?
But today we're diving straight into the microscopic world to look at the classical theory of the Raman effect. Because on a molecular level, light interacts with the physical structure of matter in some absolutely incredible, mathematically beautiful ways.
Have you ever wondered how scientists can identify a completely unknown substance like a mysterious powder or a strange liquid just by pointing a laser at it? I mean, it sounds like pure science fiction, doesn't it? But it actually relies on a very real, completely invisible dance between photons and electron clouds. And by the end of this explainer, we're going to demystify the exact machinery that makes this possible.
Okay, let's dive into this. Here is our roadmap. We'll start big picture with light meets matter. Take a quick look at the virtual state, and then really unpack the classical theory of polarization. From there, we'll break down the mathematics of scattering, figure out what makes it active, and wrap the whole thing up with the quantum perspective. Let's build this up step by step.
All right, moving into Section 1, light meets matter.
So when a beam of light hits an object, a few things can happen. It can transmit right through, it can be absorbed as heat, or it can scatter. And that scattering, that is exactly what we care about today. This brings us to Raman spectroscopy. Discovered way back in 1928 by Indian physicists C.V. Raman and K.S. Krishnan, this is an analytical technique that uses scattered light to measure a sample's vibrational energy modes. Think of it like extracting a unique chemical and structural fingerprint from a material. You shine a light, and the specific way that light scatters back tells you exactly what those molecules are doing.
Check this out. When a laser, which we're representing with that green line, hits a molecule, the vast majority of the light just bounces off elastically at the exact same wavelength. We call that Rayleigh scattering. But a tiny, tiny fraction of that light actually shifts its color. It either loses energy, shifting to a longer, redder wavelength,
which we call Stokes-Raman scattering, or, believe it or not, it can actually gain energy from the molecule, shifting to a shorter, bluer wavelength called Anti-Stokes.
So why does that tiny fraction of light change its energy? To find out, let's jump to section 2, the virtual state.
Here's what's happening. When a photon strikes, its oscillating electromagnetic field actually distorts or polarizes the molecule's electron cloud. Energy is momentarily transferred from the light to the molecule, and it forms what we call a virtual state. Now, this isn't some stable, permanent new state for the molecule. No way. It is a fleeting, highly unstable complex. Almost the exact millisecond it forms, the molecule kicks the photon right back out, re-emitting it as scattered light. And it's this incredibly fast catch and release that actually causes that energy shift.
To really grasp how this works, we need to look under the hood of the molecule itself. Section 3. Classical theory of polarization.
Okay, this simple formula right here is literally the foundation of everything we're talking about today. The induced dipole moment, or mu, equals polarizability, alpha, times the electrical field, E. Let's break that down into plain English. Think of the molecule's electron cloud like a squishy water balloon. The incoming light's electrical field, that acts like your hand's actually squeezing the balloon. So the polarizability, that alpha symbol, is simply a measure of how squishy or flexible that molecular balloon really is.
Now, what's really interesting about this is visualizing that squeezing in real time. Because the incoming light isn't a static force, right? It's a wave. It's oscillating up and down. Because of this, the light's electrical field forces the molecule's electron cloud to polarize and oscillate at that exact same incoming frequency. Basically, the molecule is forced to dance to the exact rhythm of the laser beam.
So we've got a molecule dancing to the laser's rhythm. Let's move to section 4, the mathematics of scattering. Don't worry, we're going to keep this highly conceptual.
The progression here works in 3 really logical steps. Step 1, we establish the molecule's baseline squishiness, its equilibrium polarizability. But molecules aren't just frozen in place, they naturally vibrate all on their own. So for step 2, we add the molecule's own internal vibrational frequency into the mix. This means the squishiness of the molecule is continuously, naturally changing as it vibrates. Finally, in step 3, the magic happens. We mathematically multiply these 2 oscillating waves together, the superfast wave of the incoming light and the slower wave of the molecule's natural vibration.
And here is the payoff of that mathematical expansion. Just look at that final equation at the bottom. When you expand the product of 2 sine waves using basic trigonometry, the math literally spits out 3 distinct frequency components. The theory absolutely perfectly predicts exactly what we observe in the laboratory. So, the crucial point is how those 3 mathematical components translate to actual light. That first component is the Rayleigh line. That's the light scattering at the exact original frequency, nu. But the math also gives us the Stokes line, where the scattered light is the original frequency minus the molecule's vibrational frequency. And finally, the Anti-Stokes line, which is the original frequency plus the molecule's vibration. The light has fundamentally absorbed or donated energy based entirely on how the molecule jiggles.
Let's anchor all that pure theory back to a real-world graph. This, right here, is the actual Raman spectrum of a chemical called carbon tetrachloride. See that massive peak right in the center at 0? That's our Rayleigh scattering. Absolutely no energy shift. Flanking it symmetrically on the right, you'll see the Stokes shifts peaking at specific positive values like 218 and 314. Those represent the light that lost energy. Over on the left are the much weaker anti-Stokes shifts, where the light gained energy. Because these exact number values are derived directly from the molecule's unique internal vibrations, this graph acts as an absolute, undeniable chemical fingerprint for carbon tetrachloride.
But here is the catch. Not every single molecular wiggle is going to show up on one of these graphs. Which brings us to section 5. What makes it active?
There is a golden rule here, for sure. For a molecular vibration to be Raman active, meaning it actually produces a detectable spike on our graph, the polarizability ellipsoid absolutely must change during the vibration. So imagine that squishy electron cloud we talked about earlier as a 3D balloon, an ellipsoid. As the atoms inside move around, that overall 3D balloon must change in its shape, its overall size, or its orientation. If the balloon doesn't change, we see absolutely nothing.
Check out these 2 movements side by side to really see this in action. On the left, we've got a symmetric stretch. The outer atoms pull away and then push back together. As they do, the overall size of the electron cloud changes. Because the polarizability changes, this movement gets a big green check mark. It is Raman active.
Now look at the right side, a bending motion. The atoms swing up and down, but the overall size and shape of the electron cloud's squishiness stays exactly the same throughout the entire motion. Because the change is zero, this movement is completely Raman inactive. The laser literally won't see it.
Let's move to section 6 and see how this all builds into the quantum perspective.
Up until now, we've been treating light as a continuous classical wave, and honestly, it works beautifully. But quantum mechanics gives us another perfect lens to look through. This diagram replaces those waves with distinct quantized energy levels. The incoming photon excites the molecule up from a stable ground state to that dashed virtual state line. If it drops back down to the exact same starting energy line, we get the green arrows, elastic Rayleigh scattering. But if the molecule drops back to a slightly higher vibrational energy level than it started, it holds on to some of that energy, emitting a lower energy red photon, our Stokes scatter. The quantum energy drop perfectly, beautifully mirrors our classical trigonometric math.
Which leaves us with this final thought. We started out by asking how shining a light can actually identify a mystery substance. Well, now you know the mechanics. So how does this invisible dance of photons and electron clouds shape our understanding of the entire universe? From rapidly identifying counterfeit pharmaceuticals here on Earth to rovers scanning rocks on Mars for the chemical signatures of past life, Raman spectroscopy proves that if you just understand the math of the microscopic world, the absolute deepest secrets of reality are hiding right there in the scattered light.
Absolute most fascinating secrets of the physical world. We're going to look at how light interacts with matter, and I don't mean just on a surface level. We're going deep down into the fundamental quantum level to reveal the hidden chemical secrets of the universe. It's this wild story of super rare events, shifting colors, and molecular fingerprints, all driven by a totally bizarre quantum quirk. Let's get into it.
To get us started, I want you to picture a beam of light hitting a physical object. Simple enough scenario, right? But what actually happens to that light when it strikes a single molecule? This fundamental question right here is the macro-level mystery we are about to explore today. And spoiler alert, the answer is way more complex and honestly much more beautiful than you might think.
Okay, let's really dive into this. When light meets matter, it basically has a few options. If you look at the paths here, it can transmit right through the material, kind of like sunlight through a window. It can be absorbed, which heats the material up. It can reflect right off the surface, or it can scatter. Now, the specific path it takes depends completely on the material itself and the wavelength or color of the incoming light. But today, we are focusing entirely on that last path, scattering.
So here's our roadmap for the explainer. First, light meeting matter. Second, the 1 in 10 million. Third, Stokes and Anti-Stokes. Fourth, the classical theory. Fifth, the quantum theory of Raman. And finally, reading molecular fingerprints.
Section 1. Light meeting matter, history and discovery. So, the study of how light interacts with matter is what we call spectroscopy. And back in 1928, the brilliant Indian physicist C.V. Raman, along with his research partner K.S. Krishnan, made a totally groundbreaking observation. They discovered this highly specific type of scattering that actually allowed them to measure the internal vibrational energy modes of a sample. By looking at how the scattered light changed, they realized, wow, we can actually identify completely unknown substances with this. Because, as it turns out, every chemical leaves behind its own unique, characteristic Raman fingerprint.
Section 2. The 1 in 10 million. A statistical rarity. 1 in 10 million. Let that sink in. When a beam of photons strikes a molecule and scatters, the Raman effect, which is that inelastic scattering process that actually transfers energy and gives us that awesome molecular fingerprint, only happens to about 1 in every 10 million photons. Seriously, you have better odds of winning the lottery than a photon has of undergoing Raman scattering. It is just an incredibly rare event in the microscopic world.
So you're probably wondering what happens to the other 9,999,999 photons? Well, they undergo what's known as Rayleigh scattering. Think of this as the elastic majority. In Rayleigh scattering, the photon basically bounces off the molecule, but absolutely zero energy is exchanged. The molecule's energy stays exactly the same, and the scattered photon keeps its exact original energy and wavelength. It is by far the dominant process, but since absolutely nothing changes, it doesn't really tell us much about the molecule's internal structure.
Section 3. Stokes and Anti-Stokes. Energy transfer. All right, to help visualize this, take a look at the green incoming laser light over on the left. That green wave bouncing off to the bottom right, that's our Rayleigh scattering. Same color, same wavelength, nothing exciting. But look at the red and blue waves.
These represent our 1 in 10 million Raman scattered photons. Their wavelengths have physically changed, which means their colors have actually shifted.
Now, there are two distinct ways this shift can actually happen. First up is Stokes-Raman scattering. Here, the molecule actually gains energy from the photon, getting excited up to a higher vibrational level. And since energy has to be conserved, right, the scattered photon loses that exact amount of energy, which means its wavelength increases, shifting it down toward the red end of the spectrum. The inverse of this is anti-Stokes scattering. Here, the molecule loses energy by relaxing to a lower vibrational state, and it gives that energy back to the photon. The photon gains energy, so its wavelength decreases, shifting it up toward the blue end.
Section 4. The classical theory, polarizability.
Okay, so the classical theory for all this relies heavily on a concept called polarization. Just imagine an electrically neutral molecule. It's got this cloud of negative electrons sort of surrounding the positive nuclei. Polarization is simply the extent to which that squishy electron cloud can be stretched out or distorted when you expose it to a uniform electrical field.
So if we look at the classical sequence, it basically goes like this. First, electromagnetic radiation, so light, hits the molecule. Second, the oscillating electrical field of that light polarizes the molecule's electron cloud. Third, this causes the entire molecule to act kind of like a tiny little antenna, oscillating with the exact same frequency as the incoming light. And finally, this newly formed oscillating dipole emits radiation of its own. And if the molecule happens to be vibrating internally at the same time, it actually modulates that scattered light, and boom, that's what creates those shifted Raman frequencies.
Now, don't get me wrong. The classical theory is super helpful for picturing a squishy electron cloud acting like an antenna, but it doesn't quite give us the complete modern picture. See, classical theory focuses on continuous waves and changing polarizability. To fully solve our mystery, we really need to juxtapose this with quantum theory. Quantum theory focuses on discrete, quantized energy states, highly unstable virtual states, and the exact packet-like transfer of photon energy. It's a real game changer.
Section 5. Quantum theory of Raman. Discrete energy jumps.
All right, the absolute central concept here is the virtual state. When that incoming photon strikes the molecule, it transfers its energy. But it doesn't just neatly bump the molecule up to a stable, recognized electron orbit. Instead, it forms this virtual state. And in the quantum world, this isn't a real stable orbit at all. It's a highly unstable, incredibly short-lived ghost of a complex between the photon and the molecule. I mean, it is so ridiculously unstable that the photon gets re-emitted almost immediately.
Let's actually track these discrete quantum jumps on an energy level diagram, because this brilliantly illustrates what's going on. The solid black lines down at the bottom, those are the stable energy states of the molecule. You've got your ground state and a slightly higher vibrational state right above it. Now see that dotted line way up at the top? That represents our highly unstable virtual state. Those upward arrows show the incoming photon pushing the molecule all the way up into that virtual state.
Now, let's trace the downward arrows. These represent the scattered light. On the left, Rayleigh scattering drops all the way back down to the exact original ground state, so no net change there. In the middle, Stokes scattering drops from the virtual state but stops at a higher vibrational level. The molecule kept some of that energy, meaning the scattered photon has less. And over on the right, Anti-Stokes scattering starts with a molecule that was already in an excited vibrational state. It pushes it to the virtual state, but then drops it all the way down to the lowest ground state. So the molecule lost energy, giving a nice little boost to the scattered photon. And the math here perfectly matches these visual drops. It's just so elegant!
Section 6. Reading molecular fingerprints. Reading the spectra.
Okay, so here is what the actual output from a Raman spectrometer looks like when analyzing a sample of carbon tetrachloride. That massive peak right in the dead center, 0, that's our Rayleigh scattering. Remember, it is millions of times more common, so it's huge. But look off to the right and the left, those tiny little peaks are our super rare Raman scatterings. To make this easy to read across different laser types, scientists mathematically convert the scatter position into a standardized Raman shift, measured in inverse centimeters. Basically, these peaks are the unique, undeniable fingerprint of carbon tetrachloride.
Now, you might have noticed on that last graph that the peaks on the right, the Stokes lines, were way taller than the anti-Stokes lines on the left. So why is that? Well, quantum mechanically speaking, going up or down is an equally likely process. But practically, we are dealing with an ensemble of trillions of molecules. According to the Boltzmann distribution, the vast majority of molecules naturally sit on the ground floor, their absolute lowest vibrational state at room temperature. Because they're already at the bottom, they really can only go up, which means Stokes scattering is statistically far more probable and way more intense to measure. And honestly, that brings us to the true superpower of Raman spectroscopy. By shining a laser and isolating a quantum event that only happens to 1 in 10 million photons, we can look at the Stokes shift and deduce the exact vibrational modes, the precise chemical bonds, and the unique identity of almost any substance. From checking the purity of pharmaceuticals, to detecting explosives, to literally analyzing the minerals on the surface of Mars with the Perseverance rover, this bizarre little quantum quirk is mapping our entire universe. So how does measuring a 1 in 10 million quantum energy shift allow us to map the chemical makeup of everything around us? Well, it's a profound question to ponder the next time you're just looking at a simple beam of light. Thank you so much for joining me on this explainer, and as always, keep exploring.